When you measure the joints between the massive limestone blocks that once formed the outer casing of the Great Pyramid, you find gaps averaging half a millimeter. Half a millimeter. These are stones weighing multiple tons, cut and fitted with precision that rivals modern machining. At the Serapeum of Saqqara, granite boxes weighing up to 100 tons show surface flatness measuring 2.54 microns. That's 0.0001 inches. For context, modern precision surface plates used in aerospace manufacturing achieve flatness between 0.6 and 2.5 microns depending on grade. Ancient Egyptian craftsmen working with copper chisels and stone pounders achieved tolerances that match what we consider industrial precision today. The question isn't whether this precision exists. The measurements are documented, verified, and repeatable. The question is how. How did builders working without micrometers, dial indicators, or coordinate measuring machines achieve tolerances measured in thousandths of a millimeter? This isn't a mystery that requires speculation about lost civilizations or advanced technology. It's an engineering problem with engineering solutions. Over the next 45 minutes, we're going to examine the specific mechanical principles, the material science, the geometric techniques, and the experimental archaeology that explains how ancient precision was achieved. You'll understand the self-correcting methods that create flatness without precision instruments. You'll see how abrasive mechanics naturally trend toward accuracy. You'll learn why granite behaves the way it does under grinding and lapping. And you'll discover which aspects of ancient stonework have been successfully replicated through experiment, and which aspects still resist complete explanation. This is technical analysis of ancient architectural precision. Let's examine how it actually worked. The Great Pyramid provides the most thoroughly measured example of ancient precision at monumental scale. Sir Flinders Petrie surveyed the structure between 1880 and 1882 using the best instruments available in the Victorian era. His measurements documented a base with sides averaging 230 meters in length. The variation between the longest and shortest sides measures 58 millimeters. Across 230 meters, that's a deviation of 0.025%. The corner angles measure accurate to 12 arc-seconds. An arc-second is 1/3600th of a degree. 12 arc-seconds means the corners deviate from perfect 90-degree angles by about 0.003 of a degree. These angles are virtually indistinguishable from perfect right angles using standard surveying equipment. The pyramid's alignment to true north shows an error of 3 minutes 38 seconds of arc. That's roughly 0.06 of 1 degree. J. H. Cole resurveyed the pyramid in 1925 using more modern equipment and confirmed Petrie's findings. The limestone platform beneath the pyramid structure extends across 53,000 square meters. That's about 13 acres. The platform is leveled to within 21 millimeters across its entire footprint. 21 millimeters of variance across 13 acres. Modern laser-leveled concrete foundation pads achieve similar tolerances. The difference is that modern foundations use laser transits, rotating laser levels, and electronic surveying instruments. The Egyptian 4th Dynasty builders had none of these tools, yet they achieved equivalent results. The original outer casing of the Great Pyramid consisted of highly polished Tura limestone blocks. Most of these were removed over centuries for building projects in Cairo. The few remaining casing stones at the base show extraordinary precision in their fitting. Petrie measured joint gaps averaging half a millimeter. Some joints measured even tighter. The faces of these blocks were cut straight to within 1/4 millimeter over their entire surface. These aren't small decorative pieces. Each casing stone weighs between 2 and 15 tons. The precision occurs on blocks that required teams of workers to move and position. Inside the pyramid, the king's chamber demonstrates precision in granite rather than limestone. 5 courses of granite blocks form the walls. The corners approach perfect right angles. The chamber's dimensions follow specific mathematical proportions: 20 royal cubits long, 10 royal cubits wide, and 11.18 royal cubits high. That height equals the square root of 125. The proportions aren't approximate. They're exact within the tolerance of measurement. This represents intentional geometric design executed with precision. The Serapeum of Saqqara contains 24 enormous granite boxes housed in underground tunnels. These boxes were traditionally identified as sarcophagi for sacred Apis bulls. Each box is carved from a single piece of Aswan granite. The boxes weigh between 70 and 100 tons. Christopher Dunn, a precision manufacturing engineer with over 50 years of aerospace industry experience, measured these boxes using calibrated metrology instruments. He used precision straight edges accurate to 0.0002 inches. He used calibrated squares accurate to 0.00005 inches. These are the same tools used to verify precision in modern machine shops. His measurements documented surface flatness with deviations of only 2.54 microns. That's 0.0001 inches. The interior corners of these boxes show radii of approximately 4 millimeters. The walls are parallel to each other. The walls are square to each other. All of this in solid granite, in boxes weighing up to 100 tons. For comparison, a modern Grade B granite surface plate, which would be used in a tool room for precision measurement, achieves flatness of about 2.5 microns. Grade AA surface plates used in metrology laboratories achieve 0.6 microns. The Serapeum boxes fall within the range of modern industrial precision granite work. The boxes were created sometime during Egypt's New Kingdom period, roughly 3,000 years ago. The precision has been maintained over 3 millennia because granite is dimensionally stable, but the question remains: how was this precision achieved in the first place without modern measuring instruments? The precision phenomenon isn't limited to Egypt. At Machu Picchu and Sacsayhuaman in Peru, Inca stonework demonstrates sub-millimeter fitting between irregularly shaped polygonal blocks. Some blocks have 32 angles where they interface with neighboring stones. Laser scanning of these walls confirms that joint precision extends deep into the stone interfaces. It's not just surface fitting. The precision goes centimeters into the contact zones. Archaeological studies documented mortar layers between stones measuring 1 to 1.5 millimeters thick. The famous test of inserting a razor blade into joints demonstrates that gaps are too tight for the blade to penetrate. At Pumapunku in Bolivia, even more puzzling precision appears. The H blocks at this site show approximately 80 machined faces per block. Right angles deviate by only a few millimeters over several meters of measurement. Archaeologists Jean-Pierre Protzen and Stella Nair documented precision-drilled holes 6 millimeters in diameter, identically spaced across multiple blocks. The surfaces show finishing work that Protzen described as created by techniques unknown to the Incas and unknown to us at this time. Sharp, 90-degree interior corners that appear not to have been made with hammerstones. Doubly curved surfaces with steep parabolic profiles that would challenge modern stonemasons. Multiple civilizations, separated by oceans and millennia, achieved similar levels of precision. This suggests the techniques weren't culturally specific mysteries. They were applications of universal engineering principles. The most important insight for understanding ancient precision is this: precision doesn't require precision instruments. That sounds paradoxical, but it's mathematically and physically true. Nature provides perfect references that require zero calibration. Gravity defines a perfectly vertical line through any suspended weight. Gravity defines a perfectly horizontal plane through any water surface. Geometry defines perfect right angles through mathematical relationships. And certain mechanical processes naturally create precision through self-correcting physics. The key is understanding which natural phenomena are self-defining, and how to leverage those phenomena through systematic method. Modern precision engineering inherited these principles. We've added speed and convenience through powered tools and electronic measurement. But the fundamental physics of how precision is created remains identical to what ancient builders could access. A plumb bob hanging from a string defines true vertical with absolute accuracy. No calibration needed. Gravity is the calibration. A water level shows true horizontal across any distance. The water surface naturally seeks an equipotential gravitational surface. No calibration needed. Physics is the calibration. A stretched rope approximates a straight line. Actually, it forms a slight catenary curve due to its own weight, but over practical distances the deviation is negligible. These are the building blocks of precision without instruments. Let's examine the most powerful of these self-correcting techniques. The three-plate lapping method. Imagine you want to create a perfectly flat surface. You have 2 pieces of granite and some abrasive sand. You rub the 2 pieces together with the sand between them. The abrasive particles attack the high spots where pressure is greatest. Over time, the surfaces conform to each other. Eventually, they fit together very closely. But here's the problem. They might both be curved. One surface could be convex, bulging outward. The other surface could be concave, curving inward. They'd fit each other perfectly like a bowl and a lid. But neither surface would be actually flat. You can't tell this is happening if you only have 2 surfaces to work with. This is where the 3-plate method becomes essential. Take 3 surfaces instead of 2. Call them Plate A, Plate B, and Plate C. Lap Plate A against Plate B with abrasive between them. Then lap Plate B against Plate C. Then lap Plate C against Plate A. Continue rotating through these pairings. Here's the key geometric insight. If Plate A is convex, it will try to make Plate B concave where they touch. But now you lap Plate B against Plate C. If Plate B is concave, it will try to make Plate C convex. Now you lap Plate C against Plate A. If Plate C is convex and Plate A is also convex, they can't fit together properly. The errors fight each other. The high spots on one plate create pressure points on the other plate. Those pressure points cause faster material removal. Rotating the plates during lapping redistributes where the high spots contact. The mathematics of 3 mutually conforming surfaces forces them toward flatness. It's geometrically impossible for 3 surfaces to all fit each other well unless they're all flat. This isn't speculation. This is proven mathematics. Joseph Whitworth formalized this method in England in the 1840s. He's considered the father of modern precision measurement. But the principle he formalized doesn't depend on industrial-era technology. It depends on geometry. Geometry existed 3,000 years ago just as it exists today. Understanding why the three-plate method works requires understanding how abrasive cutting functions at the mechanical level. When you place loose abrasive particles between two surfaces and apply pressure, the particles don't simply scratch randomly. They respond to the pressure distribution. Where two surfaces are closer together, pressure is higher. Higher pressure forces abrasive particles harder against both surfaces. Harder contact means faster material removal. Where surfaces are further apart, pressure is lower. Lower pressure means less aggressive cutting. The process naturally tends toward uniform contact. High spots get worn down faster than low spots. This continues until pressure distribution becomes uniform. Uniform pressure distribution only occurs when surfaces are conforming to each other. The abrasive material matters significantly. For granite with a Mohs hardness of 6 to 7, you need abrasive particles at least as hard as the granite itself. Quartz sand has a Mohs hardness of 7. This makes it suitable for granite work, though cutting is slow. Emery has a Mohs hardness of 8 to 9. Corundum also measures 8 to 9. These cut granite much more efficiently than quartz. The abrasive must be used with lubricant. Water or oil serves several functions. It keeps the abrasive particles rolling and tumbling between the surfaces rather than embedding in one surface. It clears away the material that's been ground off. It prevents heat buildup that could cause surface cracking. The wearing process happens at the microscopic level. Individual abrasive grains fracture the granite's crystal structure. Tiny chips of material break away. The surface gradually becomes smoother as larger irregularities are reduced. With fine enough abrasive and sufficient time, granite can be polished to a mirror finish. Surface roughness can reach 0.1 microns, which is mirror quality. The process requires no powered machinery. It requires abrasive material, patience, and systematic application of the method. Time is the main variable. What a powered grinder achieves in minutes, hand lapping achieves in hours or days. But the ultimate precision level is comparable. Ancient builders had access to several naturally perfect references that required no calibration or complex instruments. The stretched cord provided a straight-line reference. A tightly stretched rope or cord naturally forms close to a straight line. Technically, it sags slightly into a catenary curve due to its own weight. But for practical construction distances, the deviation from straight is negligible. Egyptian tomb paintings show rope stretchers, called harpedon apte, using cords to lay out building foundations. The cord can be used to sight along, establishing straight lines for wall placement or trench digging. Water leveling exploited gravity's perfect horizontal. A water-filled trough or channel naturally settles to a level surface. This occurs because water seeks the lowest gravitational potential. The water surface becomes an equipotential surface. Equipotential means every point on the surface has equal gravitational potential energy. In practical terms, it means perfectly level. By placing water-filled tubes or channels at different locations and ensuring the water level matches, you create a level reference across any distance. This principle was understood and used in ancient Egypt, Mesopotamia, Greece, and Rome. No calibration needed. Gravity provides the standard. The plumb bob defined true vertical with equal perfection. Suspend any weight from a cord and it aligns with the direction of gravitational force. This is, by definition, perfectly vertical. Ancient builders used plumb bobs to verify walls were vertical, to transfer points from one height to another, and to establish vertical reference lines. Again, gravity provides the calibration. These aren't approximate methods. They're physically perfect within the limits of material construction. A well-made plumb bob hanging in still air defines vertical to within arcseconds of accuracy. A well-constructed water level defines horizontal to similar precision. These tools don't require verification against other standards. They are the standards. Creating perfect right angles without surveying instruments relies on the Pythagorean theorem. In a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. If you have a triangle with sides measuring 3 units, 4 units, and 5 units, the 3 squared plus 4 squared equals 9 plus 16, which equals 25, which equals 5 squared. This only works if the angle between the 3-unit side and the 4-unit side is exactly 90 degrees. The relationship is mathematically guaranteed. Ancient builders used knotted ropes or cords with evenly spaced knots to create 3, 4, 5 triangles. Egyptian rope stretchers would lay out a rope with 12 equal intervals marked. Form it into a triangle with sides of 3 intervals, 4 intervals, and 5 intervals. The angle between the 3 side and the 4 side must be 90 degrees. This method appears in ancient Egyptian, Babylonian, Chinese, and Indian sources. It's sometimes called the rope stretcher method or the Egyptian triangle. The technique is self-checking. If you measure the diagonal and it doesn't equal 5 units, your angle isn't 90 degrees. If it does equal 5 units, your angle is mathematically guaranteed to be 90 degrees. No protractor needed. No angle measuring instrument needed. Geometry enforces the precision. This same principle scales. Use a 6-8-10 triangle for the same 90-degree angle. Use a 30-40-50 layout for large foundations. The ratio remains constant. The precision remains perfect. Modern construction workers still use this method for quick field verification. It's called the 3-4-5 rule. The mathematics hasn't changed in 3,000 years. Understanding ancient granite work requires understanding granite itself as an engineering material. Granite is an igneous rock formed from slowly cooled magma deep underground. It consists primarily of 3 minerals: quartz, which has a Mohs hardness of 7, feldspar, which has a Mohs hardness of 6, and mica, which has a Mohs hardness of 2 to 3. The overall hardness of granite measures 6 to 7 on the Mohs scale. For comparison, hardened steel measures about 5.5. Granite is harder than steel. This presents a challenge for cutting, but it also provides remarkable benefits. Granite has an extremely low thermal expansion coefficient. It expands about 3 to 5 parts per million per degree Celsius. Steel expands about 12 parts per million per degree Celsius. This means granite changes dimension with temperature about half as much as steel. This is why modern precision engineering uses granite for surface plates, coordinate measuring machine bases, and optical bench supports. Granite maintains its dimensional accuracy as temperature fluctuates. Ancient granite work created in Egypt's relatively stable climate has maintained its precision over millennia. Metal work would have expanded and contracted more dramatically with seasonal temperature changes. The crystalline structure of granite allows it to be ground to extremely smooth finishes. With progressively finer abrasives, granite surfaces can achieve roughness of 0.1 microns Ray. RA stands for roughness average, a standard measurement of surface finish. 0.1 microns RA is mirror quality. Light reflects off such a surface with minimal scatter. This level of finish is achievable with hand methods if you have fine enough abrasive and sufficient time. Granite also fractures in a somewhat predictable way. Impact from hammerstones causes localized fracturing. Controlled fracturing can rough out shapes. Then, grinding and abrasive methods smooth and refine the surfaces to final dimensions. The combination of hardness, dimensional stability, and ability to take a mirror finish made granite an excellent choice for precision work that needed to last. The effectiveness of ancient stoneworking depended critically on access to appropriate abrasives. Quartz sand was abundant throughout Egypt. Quartz has a Mohs hardness of 7, equal to or slightly harder than granite. This makes quartz sand capable of abrading granite, though the cutting rate is slow. Quartz sand was certainly used for much ancient stonework, but for harder stones and for precision work, ancient craftsmen used higher performance abrasives. Emery is a naturally occurring mixture of corundum and magnetite with other minerals. Corundum is aluminum oxide with a Mohs hardness of 9. Only diamond, at hardness 10, is harder than corundum. Emery deposits had been mined on the Greek island of Naxos for over 2,000 years before the Roman era. Egyptian sources for corundum-bearing materials existed in the southern eastern desert. The Hafafit deposit contains corundum in metamorphic rocks. Ancient Egyptians had access to these deposits, and evidence suggests they used corundum-based abrasives. Scanning electron microscope analysis performed by the Metropolitan Museum of Art examined material from an ancient drill hole. The sample came from Amarna, dating to approximately 1353 to 1336 BCE. The analysis identified angular corundum grains 50 to 200 microns in size. These grains were surrounded by calcite and bronze corrosion products. This provides direct physical evidence that Egyptians used corundum as an abrasive with copper tools. The importance of this finding cannot be overstated. It resolves a long-standing debate about whether copper tools could effectively work granite. Copper alone cannot cut granite. Copper with quartz sand can cut granite slowly. Copper with corundum or emery can cut granite efficiently. The tool material matters less than the abrasive material. The copper or bronze provides a backing that holds and guides the abrasive. The abrasive does the actual cutting. Gorelick and Gwinnett at the University of Pennsylvania Museum conducted definitive experiments on ancient drilling techniques in the 1980s. They tested various tool and abrasive combinations on granite samples that matched 4th Dynasty sarcophagus material. The goal was to determine which combinations produced the characteristic concentric cutting lines visible on ancient drill cores and saw cuts. These concentric striations appear consistently on Egyptian stonework and have been the subject of speculation for over a century. Their experimental setup used copper tube drills modeled on ancient tool types. They tested wet sand as an abrasive. They tested crushed quartz. They tested emery and corundum. They carefully documented the results. Wet sand, despite being Mohs hardness 7, did not produce concentric cutting lines. The surface it created was rough and irregular. Crushed quartz also failed to produce the characteristic striations, even with lubricant. Emery used with water or oil produced clear concentric cutting lines that closely matched ancient examples. Corundum used with water or oil produced similar results. Diamond abrasive also produced the lines, and cut fastest, being 4 times harder than corundum. But diamond wasn't available to ancient Egyptians as far as we know. The conclusion was clear. Ancient Egyptians used emery or corundum-based abrasives with copper tools to achieve the precision drilling and cutting visible on their stonework. This explains how copper tools, which are softer than granite, could effectively work granite. The copper wasn't doing the cutting. The corundum particles were doing the cutting. The copper tube or saw blade provided the backing and guidance. Water or oil kept the abrasive particles active and cleared debris. This represents sophisticated understanding of materials and abrasive cutting mechanics. The Egyptian measurement system centered on the royal cubit. Surviving cubit rods show lengths ranging from 523.5 millimeters to 529.2 millimeters. The average royal cubit measured approximately 526 millimeters, about 20.7 inches. The cubit was subdivided into 7 palms. Each palm contained 4 fingers. This gave 28 digits total per cubit. 1 digit equaled approximately 18.8 millimeters. The smallest standard subdivision was 1/16 of a digit. This measures approximately 1.2 millimeters. So the Egyptian measurement system had theoretical resolution to about 1 millimeter. Ceremonial cubit rods have been found with inscriptions recording adjustment values. These adjustments were specific to different nomes, the administrative regions of Upper and Lower Egypt. 22 nomes in Upper Egypt and 17 in Lower Egypt each had slightly different cubit lengths recorded. This suggests sophisticated understanding that measurement standards needed to be consistent and verified. Ancient texts indicate that working cubit measuring sticks were checked against the royal master cubit at regular intervals. Some sources suggest this verification happened at every full moon. Royal architects were responsible for maintaining measurement accuracy across construction projects. The question is how accurately these measurements could be transferred and applied. Having a measurement system with 1 millimeter theoretical resolution doesn't automatically mean work was executed to that tolerance. Modern measurement systems have resolution far exceeding what's achieved in practice. Transfer errors, marking errors, cutting errors all accumulate. But the system provided the framework for millimeter-level precision if the craftsman had the skill to apply it. And the physical evidence demonstrates they did have that skill. The tight joints visible at sites from Egypt to Peru were achieved through iterative trial fitting using marking compounds. This technique remains in use in modern precision machine shops. It's called scraping or lapping with bluing. The basic principle is simple but powerful. Apply a thin film of marking compound to a known reference surface. Bring the workpiece into contact with the reference surface using only gravity pressure. The marking compound transfers to high spots on the workpiece. These high spots now show as colored marks. Remove material from the high spots through grinding, scraping, or pounding. Clean both surfaces and repeat the process. As the surface improves, thin the marking compound film. Thinner film reveals smaller deviations. Continue until the desired precision is achieved. Red ochre, an iron oxide pigment, has been used as a marking compound since ancient times. It's naturally occurring, easily prepared, and highly visible against stone. Joseph Whitworth referenced the use of red ochre for precision scraping in his 1840s publications. The technique predates him by centuries at minimum. Modern machinists use Prussian blue for the same purpose, but the principle is identical. For granite work, the marking compound could be applied to a reference surface that had already been lapped flat using the three-plate method. Or 2 surfaces could be fitted to each other directly. Initial fitting might use coarse abrasive to remove material quickly. Later stages would use progressively finer abrasive. Final fitting might use very fine emery or corundum to achieve the last fraction of a millimeter. The gravity pressure is important. You're not forcing the surfaces together. You're allowing them to touch under their own weight. This ensures the marking reveals actual contact points rather than pressure deformations. For large blocks, gravity provides substantial pressure just from the stone's mass. A 1-ton block provides enormous even pressure across its contact surface. Modern precision scraping aims for 10 to 36 contact points per square inch as a finished surface. Each contact point indicates a high spot that has been brought into conformance with the reference. More contact points mean better overall flatness. This method scales from small precision parts to massive architectural stones. The physics remains the same regardless of size. Jean-Pierre Protzen conducted extensive experimental archaeology on Inca stone working techniques in the 1980s. He worked at Ollantaytambo in Peru, using tools and methods that would have been available to Inca craftsmen. For hammerstones, he used quartzite river cobbles. These measured up to 10 kilograms in weight. Quartzite has similar hardness to the andesite and granite the Incas commonly worked. He found that striking at angles of 15 to 25 degrees while rotating the hammerstone at impact maximized material removal. This technique causes controlled fracturing of the target stone's surface. Repeated blows gradually shape the stone. For finishing work, he used the trial and error fitting method with marking compounds. The process he documented was straightforward. Shape the block roughly using hammerstone percussion. Test fitted against the neighboring stones already in place. Lower the block into position and mark where high spots prevent proper seating. Lift the block and remove material from the marked high spots. Test fit again. Repeat until the fit is acceptable. Protzen found this process worked well and achieved precise fits with little effort and in short time for stones of manageable size. He successfully created tight-fitting joints that matched Inca work. This explains the polygonal masonry characteristic of Inca walls. Rather than forcing stones into regular rectangular shapes, Inca masons fitted stones to their natural irregular shapes. This minimized material removal. It also created interlocking patterns that provide exceptional earthquake resistance. The irregular geometry allows stones to shift millimeters during seismic events, then settle back into position. Rectangular coursed masonry can fail catastrophically in earthquakes as uniform horizontal joints provide slip planes. Polygonal masonry distributes forces through three-dimensional interlocking. However, Protzen never attempted this process with the largest polygonal blocks visible at sites like Sacsayhuaman. Some of these blocks exceed 100 tons and have 32 or more angles where they interface with neighbors. The logistics of repeatedly lifting, testing, marking, adjusting, and repositioning such massive stones remain unclear. Some researchers have proposed that stones were scribed and shaped while suspended on scaffolding. This would avoid repeated heavy lifting but requires extraordinary spatial visualization to execute the complex three-dimensional fitting. The technique that worked for smaller stones may not scale directly to the largest examples. Dennis Stocks conducted comprehensive experimental archaeology testing over 250 reconstructed ancient tools. His work, published in Experiments in Egyptian Archaeology in 2003, provides the most detailed documentation of ancient stoneworking techniques. For drilling granite, he used copper tube drills. These consisted of hollow copper tubes that rotated while abrasive cut the stone. Using quartz sand as abrasive, he successfully drilled granite. The process produced characteristic concentric striations approximately 0.25 millimeters wide and deep. These matched the appearance of striations on ancient drill cores. The cutting rate was approximately 5.2 cubic centimeters of granite removed per hour. To drill a hole 6 centimeters deep required approximately 20 hours of continuous work. This is slow by modern standards, but entirely practical given unlimited labor time. The drill tube itself gradually wore away. Copper is soft compared to granite, and the abrasive wears both the granite and the copper. But copper was relatively abundant and recyclable. Worn tools could be melted down and recast. The drilling process requires steady rotation and consistent downward pressure. The weight of the drill mechanism itself can provide the pressure. For larger drills, additional weight can be added. Workers rotate the drill using a bow drill mechanism or a crank, or direct hand rotation for large tubes. The abrasive must be continuously replenished with fresh material and lubricant. Water keeps the quartz particles rolling and carries away granite powder. Without water, the abrasive particles would quickly embed in the copper and stop cutting. Stocks found that emery or corundum abrasives increased drilling speed significantly compared to quartz sand. This aligns with the Penn Museum findings about concentric striations. The harder the abrasive, the faster the cutting, up to the practical limit where the abrasive becomes too expensive or difficult to obtain. The technique absolutely works. It's been proven through multiple independent experimental programs. The question is not whether copper tube drills can make holes in granite. They demonstrably can. The question is whether all aspects of ancient drilling are fully explained by this technique. Stocks also tested copper saws with abrasive for cutting granite. He successfully cut slots 3 centimeters deep and 95 centimeters long in granite over approximately 14 hours. The copper blade wore away by 7.5 millimeters per cut. This blade loss is acceptable given copper's relative abundance. The sawing mechanism works similarly to drilling. The copper blade doesn't cut the granite directly. The blade serves as a backing to hold and guide abrasive particles. Downward pressure forces the abrasive between the blade and the stone. The particles roll and fracture the granite's crystal structure. Back and forth motion of the blade continuously brings fresh abrasive into the cutting zone. Water or oil lubricant serves 3 functions. It keeps abrasive particles mobile rather than embedded. It clears away granite powder and broken abrasive from the cut. It prevents heat buildup that could crack the stone or degrade the abrasive. For cutting large blocks, the saw would be a copper blade up to several meters long. Multiple workers could operate a 2-person saw similar to a modern 2-person crosscut saw for timber. The weight of the blade and the saw frame provide cutting pressure. Additional weight can be added to the saw frame if needed. Cutting entirely through a large block would take many days. But again, time was available. A project lasting decades allows weeks or months for individual sawing operations. The Stocks experiments demonstrated that all the basic stoneworking operations, drilling, sawing, grinding, polishing, could be accomplished with copper tools and abrasive. The rates are slow by modern standards but entirely practical given the timescales and labor forces available. While most ancient stoneworking has been successfully explained and replicated, one significant anomaly persists. Petrie documented a granite drill core, now in the Petrie Museum designated UC 16306, which shows spiral grooves suggesting rapid feed rate. If these grooves are truly spiral, they imply the drill advanced through the granite at 0.100 inches per revolution. That's 2.5 millimeters per rotation of the drill. For comparison, Modern diamond-tipped drills rotating at 900 RPM achieve approximately 0.0002 inches per revolution. The ancient implied rate would be 500 times more efficient than modern diamond drilling. Modern experimental replication using copper and sand achieves perhaps 0.001 inches per revolution at best. That's still 2 orders of magnitude slower than what the Petrie core suggests. Several explanations have been proposed. Some researchers argue that Petrie misinterpreted horizontal striations as spiral marks. If the marks are concentric rings rather than a continuous spiral, the feed rate anomaly disappears. Others suggest that ancient craftsmen used techniques involving higher pressure, different abrasives, or methods not yet identified in experimental archaeology. Some alternative researchers point to this as evidence of technology beyond what we understand ancient Egyptians to have possessed. The honest assessment is that this remains unexplained. Either the ancient technique was substantially different from what experimental archaeology has tested, or the interpretation of the physical evidence needs revision. Core UC 16306 can be examined at the Petrie Museum. Multiple researchers have studied it. The debate continues about what the marks actually represent and what drilling technique produced them. This represents a genuine gap in our understanding. Not all aspects of ancient precision work have been fully replicated or explained. Acknowledging this is important for intellectual honesty. In 1992, the television program Nova sponsored a pyramid-building experiment at Giza. Egyptologist Mark Lenner and stonemason Roger Hopkins led the project. The goal was to build a small pyramid using only tools and techniques available to ancient Egyptians. They constructed a pyramid 6 meters high over 3 weeks. The structure used 186 limestone blocks averaging 2.2 tons each. 12 quarrymen produced 8.5 stones per day over 22 days. This demonstrated that stone production rates were practical even with primitive tools. For moving blocks, they found that 12 to 20 people could pull a 2-ton stone on wooden sledges running on tracks lubricated with water or milk. Water lubrication of sandy surfaces has been experimentally shown to reduce friction dramatically. For lifting blocks, they used Martin Eisler's levering method. Wooden levers and cribbing allowed blocks to be raised 1 tier in approximately 90 minutes. This involved levering one edge up, inserting blocking, levering the other edge up, inserting more blocking, and repeating until the block reached the desired height. The method worked but required substantial timber resources. The experiment successfully demonstrated that the basic operations of quarrying, moving, and lifting stones were achievable with ancient technology. However, the project failed to achieve the precision jointing characteristic of ancient Egyptian work. Hopkins acknowledged that the joint quality could likely improve with practice. This is a telling observation. The experiment team had 3 weeks. Ancient Egyptian craftsmen had careers spanning decades. They trained from childhood in craft traditions passed through families. The precision wasn't achieved through individual trial and error. It was achieved through accumulated craft knowledge refined over generations. The Nova experiment proved basic feasibility but highlighted the importance of skill development that modern experiments can't easily replicate. A contrasting experiment occurred in 1978 when Waseda University in Japan attempted to build a pyramid using ancient methods. The project was intended to demonstrate the difficulty of pyramid construction and test various theories. The team had to repeatedly scale back their goals. Their initial target was a pyramid 20 meters high. This was reduced to 10 meters. Their target stone weight was 4 tons. This was reduced to 1 ton. They began with primitive chisels for quarrying but found progress too slow. They resorted to using electric saws. They attempted to move stones using human labor alone. 50 workers struggled to move single stones more than a few centimeters. They built an iron railway to transport stones. Even with rail transport, the work proved extremely difficult. Eventually, they had to use cranes and helicopters for lifting. The Egyptian government halted the project. It was clearly not demonstrating ancient methods at that point. The Japanese experiment demonstrated through failure just how remarkable ancient Egyptian achievements were. What appears straightforward in theory: quarry stones, move them, stack them, proves extraordinarily difficult in practice. The fact that ancient Egyptians accomplished this at monumental scale, with precision, without modern equipment, represents genuine engineering accomplishment. The experiment wasn't without value. It vividly illustrated the challenge. Sometimes demonstrating what doesn't work is as informative as demonstrating what does work. At Pumapunku in Bolivia, Jean-Pierre Protzen and Stella Nair reached a striking conclusion in their published research. To obtain the smooth finishes, the perfectly planar faces, and exact interior and exterior right angles on the finely dressed stones, ancient builders resorted to techniques unknown to the Incas and to us at this time. This represents academic honesty about the limits of current understanding. Protzen is not a sensationalist. He's a trained archaeologist and architect who has conducted extensive experimental work. His conclusion that sharp 90-degree interior angles were most likely not made with hammerstones comes from practical experience attempting to replicate the work. The steep, parabolic curves on doubly curved lintels would tax any stonemason's skills today, even with modern tools. The precision-drilled holes 6 millimeters in diameter, identically spaced across multiple blocks, have no clear production method. The holes are too regular for hand drilling. They appear machined. Yet no evidence exists of the machinery that would produce such regularity. This doesn't mean the holes couldn't have been produced with ancient techniques. It means the specific technique hasn't been identified or successfully replicated. There's a difference between impossible and unexplained. Unexplained simply means our current experimental archaeology programs haven't found the method yet. Perhaps the technique was specialized, closely held by master craftsmen, and lost when those individuals died. Perhaps it involved tools or methods that haven't been preserved or haven't been correctly interpreted from archaeological evidence. Perhaps it required skill levels that modern stonemasons, who work with different materials and different goals, simply haven't developed. The honest position is to acknowledge which aspects we can explain through replication and which aspects resist current explanation. Christopher Dunn brings a different perspective to ancient precision than traditional archaeologists. He worked in aerospace manufacturing for over 50 years. His career involved precision machining of components to extremely tight tolerances. When he measured the Serapeum boxes using the same metrology instruments he used professionally, he found tolerances that matched modern industrial standards. His conclusion is that ancient Egyptians possessed lost technology, not alien technology, not mysterious energy sources, but sophisticated mechanical techniques that were more advanced than mainstream archaeology currently acknowledges. He doesn't claim to know what those specific techniques were. He argues that the physical evidence of precision demands explanation, and that the explanations commonly offered by archaeologists don't adequately account for the measured tolerances. From an engineering perspective, achieving 2.5 micron flatness on granite surfaces requires extremely controlled processes. Modern precision lapping achieves this through carefully controlled pressure, carefully graded abrasives, and rigorous measurement verification at multiple stages. Could ancient craftsmen have developed analogous processes through empirical discovery? Possibly. The three-plate method is a self-correcting process that doesn't require understanding the underlying mathematics. An observant craftsman could discover through trial and error that working three surfaces together produces better results than working two surfaces. Could they have developed pressure control techniques, abrasive grading procedures, and quality verification methods that approached modern metrology shop practices? This stretches credibility somewhat, but it doesn't violate physics. Dunn's contribution is bringing precision manufacturing expertise to the analysis. His measurements are credible. His interpretation that this represents sophisticated technology is his professional opinion based on decades of experience. Whether that technology was lost ancient knowledge or represents capabilities we haven't properly understood remains debated. The Uncharted X project, led by researcher Ben Van Kerkwijk, used structured light 3D scanning to analyze pre-dynastic Egyptian stone vases. The vases examined were carved from granite and diorite. These are among the hardest stones worked by ancient Egyptians. The scans were analyzed by professional precision machinists using aerospace-grade metrology equipment. The analysis revealed geometric precision within fractions of a micron. Radial traverse patterns were identified that suggested systematic machining processes. Mathematical ratios appeared in the proportions of multiple artifacts. Run-out tests on one vase showed accuracy within half the thickness of a human hair. Run-out measures how much a rotating object wobbles. Low run-out indicates high precision in circular symmetry. Achieving this in hand-carved stone requires either extraordinary skill or systematic method. The most challenging observation is the production scale. Jean-Philippe Loer, who excavated extensively at Saqqara, recorded over 50,000 stone vases. These weren't crude pottery equivalents. Many were precision-carved hard stone with complex geometries. Hollow interiors sometimes had narrower openings than the maximum interior diameter. This means the interior couldn't have been accessed by straight tools. Some method of reaching around corners or working through restricted access was required. The concentration of these vases in pre-dynastic and early dynastic periods suggests they were produced within a few generations. 50,000 precision artifacts in hard stone in a relatively short time span. This strains the craft workshop model where individual master craftsmen spend weeks or months on single pieces. It suggests more systematic production methods, perhaps multiple stages with specialized workers for each stage. Perhaps jigs or guides that allowed less skilled workers to reproduce complex geometries. Perhaps techniques that modern researchers haven't identified because they didn't leave obvious archaeological traces. The vases exist. The precision is measurable. The production scale is documented. The how remains partly mysterious. Joseph Davidovich proposed an alternative explanation for some Egyptian stonework precision. The geopolymer hypothesis suggests that pyramid limestone blocks were cast in place using ancient concrete. The proposed mixture would include crushed limestone, kaolinite clay, lime, natron, and water. These ingredients react to form a limestone-like solid that hardens in place. A 2006 study published in the Journal of the American Ceramic Society examined pyramid stone samples. Michel Barsoum at Drexel University led the research. The study identified mineral compounds and air bubbles in the samples that do not occur in natural limestone. The finding was published in a peer-reviewed scientific journal. If pyramid blocks were cast rather than quarried, this would elegantly explain several observations. Extremely tight joints between blocks could result from casting blocks directly against their neighbors. The slight variation in limestone composition from block to block could result from batch-to-batch mixing differences. The absence of chisel marks on interior surfaces could result from molding rather than carving. However, the hypothesis faces significant challenges. Most geologists who have examined pyramid stones conclude they are natural limestone based on fossil content and stratification. Zahi Hawass and other mainstream Egyptologists call the theory unlikely and completely unproven. The presence of fossil shells in pyramid blocks suggests natural limestone rather than reconstituted material. Importantly, the geopolymer hypothesis doesn't address granite work at all. The Serapeum boxes, the King's Chamber, the granite vases. These are clearly carved from natural granite, not cast. So, even if some limestone blocks were cast, which remains highly disputed, this doesn't explain the granite precision work. The hypothesis represents alternative thinking about ancient construction methods. The peer-reviewed findings from Barsoum's research have not been definitively refuted, but neither have they been widely accepted by the archaeological community. It remains a minority position requiring additional evidence. Understanding ancient achievement requires understanding modern precision standards. Granite surface plates used in modern metrology are classified by grade based on their flatness tolerance. Grade AA plates, used in metrology laboratories for the most precise work, achieve flatness of approximately 0.6 microns. Grade A plates, used for high-precision manufacturing, achieve approximately 1.2 microns. Grade B plates, used in tool rooms for precision work, achieve approximately 2.5 microns. The Serapeum boxes measured at 2.54 microns fall within the Grade B tolerance. This is industrial precision. This is the level used for manufacturing precision components. Modern hand scraping, a manual technique still used for reconditioning machine tool ways and precision surfaces. TARS achieves flatness around 1.3 microns. Hand scraping involves using a precision scraper to remove minute amounts of material from high spots identified with marking compound. The technique requires significant skill but no powered machinery. Practitioners of traditional hand scraping note that it can achieve surfaces flatter than most grinding operations over long surfaces. This demonstrates that manual methods can exceed machine tolerances when sufficient skill and time are applied. The key insight is that precision didn't require the Industrial Revolution. The physics of creating flat surfaces through lapping, scraping, and iterative refinement work identically whether performed in 2000 BCE or 2025 CE. Modern technology provides speed. A computer-controlled grinder achieves in minutes what hand lapping achieves in days, but the ultimate precision level is comparable. Ancient builders had resources modern industry largely lacks: unlimited skilled labor organized over decades. Craftsmen trained from childhood in specialized family traditions. Project timelines measured in pharaoh's reigns rather than fiscal quarters. The Great Pyramid's 20-year construction timeline allowed enormous time per individual block for checking, fitting, and refinement. With approximately 2.3 million blocks in 20 years, That's roughly 1,460 daylight work hours per block placement cycle. Time for repeated trial fitting. Time for progressive grinding and polishing. Time to verify precision at each stage. Modern construction operates under completely different constraints. Speed is prioritized. Labor is expensive. Projects have tight schedules. Precision is achieved through powered tools and electronic measurement rather than patient iteration. But patient iteration can achieve equal or better results given unlimited time. Several aspects of ancient precision stonework genuinely resist complete explanation even with generous assumptions about skill and time. The drill core feed rates remain problematic. If Petrie's interpretation of spiral grooves is correct, the implied feed rate of 0.100 inches per revolution hasn't been approached in modern replication attempts. Experiments typically achieve 1/100th to 1/50th of that rate. Either ancient techniques were dramatically more efficient than we've yet replicated, or the interpretation of the physical evidence needs revision. The production scale of precision vases challenges simple craft models. Over 50,000 hard stone vases with complex geometries concentrated in a few generations implies systematic production methods beyond individual artisans spending months per piece. Some form of standardization, possibly involving guides or jigs, seems necessary to explain the output. But no such guides or jigs have been identified archaeologically. The Serapeum box internal corners present extreme difficulty. Achieving 4 mm radii in corners of boxes with micron-level flatness and parallel walls represents capabilities at the edge of what hand methods should achieve. Known techniques could theoretically accomplish this. But experimental archaeology hasn't successfully replicated it. The gap between theory and practice remains. Pumapunku's sharp interior, 90-degree angles, and precisely spaced drill holes resist explanation through known stoneworking methods. Protzen's assessment that techniques remain unknown to us at this time is academically honest. These aren't impossibilities that require invoking advanced civilizations or extraterrestrial intervention. They may simply be techniques that were specialized, closely held, and lost when the craftsmen who knew them died. The parallel with Damascus steel is instructive. Medieval Damascus steel was produced through techniques that created exceptional blade properties. The technique was lost for centuries. It wasn't mysterious or magical. It was a specific process that wasn't written down and wasn't passed on. Modern metallurgists eventually recreated it through experimental archaeology and materials analysis. But for several hundred years, it was a genuine unknown. Ancient precision techniques may be in a similar category, achievable through methods within human capability. But methods that haven't been preserved in archaeological record or haven't been correctly interpreted. The study of ancient precision stonework provides several important engineering lessons. First, precision doesn't inherently require precision instruments. Self-correcting methods like three-plate lapping create accuracy through geometric principles rather than measurement. Natural references like gravity and water provide perfect standards requiring no calibration. Second, material properties matter enormously. Granite's low thermal expansion and ability to be ground to mirror finishes made it ideal for precision work intended to last millennia. Understanding material behavior allows exploitation of those behaviors. Third, abrasive mechanics follow universal principles. Harder abrasive cuts, softer material. Loose abrasive under pressure naturally trends toward uniform contact. These principles work identically across centuries. Fourth, time and skill can substitute for powered machinery. What modern tools achieve through speed, ancient craftsmen achieved through patience. The precision levels are comparable. The time investment differs by orders of magnitude. Fifth, systematic method beats random trial and error. The three-plate method works because it's systematic. Trial fitting with marking compounds works because it's systematic. These aren't lucky discoveries. They're applications of method to achieve repeatable results. Sixth, craft knowledge accumulates over generations. Individual experiments over weeks or months can't replicate expertise built over lifetimes and passed through family lines. The NOVA experiment demonstrated feasibility but couldn't match ancient precision. The skill gap is real. Finally, some techniques may be genuinely lost. Not all knowledge is preserved. Specialized methods held by small groups of master craftsmen can disappear entirely if not passed on. This doesn't make them impossible or mysterious. It makes them historical casualties of discontinuity. Ancient builders achieved sub-millimeter precision in granite stonework through application of first principles physics. Gravity defined vertical and horizontal. Geometry enforced right angles. Abrasive contact naturally trended toward flatness when applied systematically. Iterative refinement converged on precision through repeated testing and adjustment. No mysterious technology required. No lost civilization needed. Deep understanding of material behavior. Systematic application of self-correcting methods. Patience measured in years rather than hours. These explain the vast majority of ancient precision work. The Serapeum boxes with their 2.5 micron flatness represent the extreme edge of what copper tools, stone pounders, and abrasive methods can achieve. But they don't exceed what those methods can theoretically accomplish. The Great Pyramid's casing stones with half-millimeter joints demonstrate mastery of trial-fitting techniques. The Inca polygonal masonry shows sophisticated understanding of stone properties and fitting methods. Modern experimental archaeology has validated the core techniques. Copper with corundum can drill granite. Bronze saws with emery can cut granite. 3-plate lapping can achieve micron-level flatness. Trial fitting with marking compounds can create tight joints. These have all been proven through replication. What hasn't been fully replicated is the scale and consistency. Producing thousands of nearly identical precision artifacts strains simple workshop models. Achieving the best ancient precision at full scale and full complexity remains an aspiration rather than an accomplishment. Certain specific aspects remain incompletely explained. The drill core feed rates if Petrie's interpretation is correct, the vase production scale and geometric complexity, the Serapeum internal corner precision, the Puma Punku machined features. These represent genuine gaps in understanding. They don't require abandoning physics or invoking advanced technology. They may reflect techniques we haven't rediscovered. They may reflect skill levels we haven't developed. They may reflect methods that didn't leave archaeological traces we've correctly interpreted. The knowledge gap works in both directions. Ancient craftsmen may have used techniques we haven't rediscovered. We used techniques they couldn't have imagined. Neither invalidates the other. Engineering requires humility about what we don't know while building on what we do know. What we do know is that sub-millimeter precision in granite was achieved 3,000 years ago. We know it was achieved through methods that follow physical principles. We know many of those methods because we've successfully replicated them. We know some aspects remain mysterious not because they're impossible, but because we haven't yet found the complete explanation. The viewer has now gained concrete understanding of self-correcting geometric techniques, abrasive mechanics, material properties, measurement systems, trial fitting processes, and experimental replication results. You understand how precision was possible without modern instruments. You understand which techniques have been proven and which remain partly unexplained. You've gained engineering principles that explain ancient achievement without requiring speculation. That's the value this analysis provides. Understanding over mystery. Mechanics over mysticism. Physics over speculation. Ancient precision demonstrates human engineering ingenuity applied with extraordinary patience and skill. It deserves analysis that matches that level of rigor.